In this video, I'm going to go over sample size calculations for cohort studies. So just to start with, there's two ways to go about it. It kind of depends on whether you're doing a cohort study where the outcome is binary, like having lung cancer or not having it. And it's a bit different if your outcome is continuous, like for linear regression, something like cholesterol concentration or something like that. But this is the one for when the outcome's binary, and just kind of going over the parameters. N here is the number exposed, so you got to remember that this number that this equation spits out isn't the total sample size needed, it's just the number of exposed individuals needed, and you can figure out the total using this parameter R here, which is how you account for the ratio of unexposed to exposed individuals in the population. So the two easiest parameters to come up with are Z alpha here, your confidence, which is usually 1.96 for 95%, and Z beta here is typically 0.84 for a power of 80%. And yeah, that's typically the confidence and power that people are looking for. P here is the prevalence of the outcome. R, like I said before, is the ratio of unexposed to exposed individuals in the population. And D is a magnitude of is the magnitude of difference we want to detect, usually a difference in proportion, so like a risk difference. So just in an example to illustrate the calculation, we're doing a cohort study looking at low physical activity as a dichotomous thing, low versus high, and high blood pressure, which is also dichotomous, low versus high. And the prevalence of high blood pressure is 5%, and 40% of people engage in low physical activity. We want to be able to detect a relative risk of 3 with 95% confidence and 80% power. So pulling information out of that question, we know that the prevalence of the outcome is 5%. We want to be able to detect a relative risk of 3. Z alpha and Z beta are their usual values. R is the ratio of unexposed to exposed. It takes a little bit of work to figure out. So we know that 40% of people engage in low physical activity, so 40% of people are exposed, and you can only be one of those two things, so we know that 60% of people are unexposed, so 60 or 0.6 over 0.4 or 60 over 40 comes out to 1.5. D is the magnitude of difference we want to detect, and that will take a little bit more work to figure out. So remember here we were talking about P. P is the prevalence of the outcome in the population. P1 and P0 are a weighted average of P, so it's the P1 is the risk of disease in the exposed group, and P0 is the risk of disease in the unexposed group. So just to illustrate what that means, this is a typical 2x2 table for a cohort study where we have the number exposed and unexposed, and the number of diseased and not diseased, and we have the number of each combination. So P1, like I said, is the risk of disease in the exposed group, or the proportion of the exposed group that are diseased. So you have the number of exposure positive that are diseased, A, over all of the number that are exposure positive, A plus B. And for P0, it's the risk of disease in the unexposed group, so we have the number of disease that are not exposed, C, over the total number that are not exposed, which is C plus D. And you'll notice that this is a risk difference, because P1 here is the risk in the exposed, P0 is the risk in the unexposed, so that's a measure of effect, this risk difference. Also, it might look familiar because P1 over P0 is the relative risk, the risk in exposed over the risk in not exposed. So using that, we can find D. So we have two unknowns and two formulas here. This is a formula I haven't shown yet, so this is how P is a weighted average of P1 and P0. And yeah, so we have two equations and two unknowns, so we know P and R, and we know the relative risk, but we don't know P1 or P naught, and we don't know P1 or P naught here either. So what we can do is solve for the unknown in one equation. So P1 equals relative risk times P naught, and sub that into the other one. So we have a relative risk of 3, so we know from this P1 is 3 P naught, so we can sub that in for P1. And when we're working this out, basically we can solve for P naught just with algebra and get 0.028, and then sub this P naught back into the other equation to get P1 of 0.084. So what that lets us do is solve for D, taking the risk difference here. And now we have everything we need to sub into that equation. We have our Z alpha, Z beta values, prevalence, 1 minus prevalence, R plus 1, our absolute difference in risk, and R again. So yeah, we can find out the number exposed, which comes out to 198. And we also know that the ratio of unexposed to exposed is 1.5. So that lets us figure out the number of unexposed we'll need, 297, and adding that together, we would have a total required sample size of 495. The other situation is when you have a continuous outcome. So here a lot of the parameters, well, some of them mean the same thing, so Z alpha and Z beta will have the same interpretation. Now we have, before we represented the variability in the outcome with a proportion, but now we would represent that with the variance of the outcome in the population. R is still a proportion of unexposed to exposed. D here is now a magnitude of difference we want to detect, but we have a situation now where we have an exposure positive and exposure negative group, but the outcome is continuous, so we're comparing a difference in means now. So in this example, we're doing a cohort study looking at fiber intake, high versus low, and BMI. And we want to be able to detect a difference in BMI of 0.5 with 95% confidence and 80% power. And the prevalence of deficient fiber intake is 20%, and the variance of BMI in the population is 2. We have Z alpha and Z beta. We have the variance. Be careful if you're given the standard deviation. We have the prevalence of the exposure, so yeah, 20%. R is unexposed over exposed, so we have 20% that are exposed, and you can only be one of those two, so 80% are 80% are unexposed, so 0.8 over 0.2, R comes out to 4. And as far as D, we said that we wanted to be able to detect a difference in the mean BMI of 0.5, which is already an absolute difference in means. And just plugging all that in and solving for N, we come up to 79, and this is still the number exposed. So now we're able to find the total number by subbing in 79 into our equation here to come out with 316. So our total sample size would be 395. So there's some other things I wanted to talk about with sample size, with cohort studies. Remember at this stage we used this formula, and I said that it's a weighted average of P1 and P naught. This is really what this is, but you could have done this more directly by just knowing that, it came out to 0.028, by just knowing that 40% of the exposed, 40% of the population is exposed and 60% is not exposed. And since the population is composed of these two groups, and we know the overall prevalence of the outcome, we can just take a weighted average, because any difference of the total to just a direct mean of these two can be accounted for by just, instead of just doing P1 plus P naught divided by 2, doing a weighted average. And it comes out to 0.028 as well. Also, you might have a fixed number of people, and you want to figure out the power that you have with that amount of people, so you can rearrange for Z beta to do that. And then let's just say you get a z beta value of 0.0 or sorry 0.84. We'd find 0.8 in this, and then find 4, so 80% power. You also might be given a sample size and you're looking for power, but they tell you this is the total sample size and 10% are exposed. Remember that when you're working with this formula, you have to put the number exposed, so you'd put 200 in there. Non-dichotomous exposures are common. That both formulas I showed you today have they rely on a proportion here, or yeah, they rely on there being an exposure positive and exposure negative group. But if you're interested in something with a continuous distribution, like height here, I think was what I did. Yeah, you can split the population in half, and you would determine or estimate, like you'd come up with an expected value for the risk in those that are above the median versus those that are below the median or mean, and that's one way you could work out P1 and P naught. Another option would be to split the population into quartiles, and in that case it would be ideal to look for the greatest contrast when boiling it down to a comparison of 2. So the best option would be to compare the 4th quartile to the lowest, the 1st quartile. And I guess in this case, being short is exposure positive, so less than 160 centimeters, that quartile is exposure positive, and those above 80 centimeters are the unexposed. But we have to recognize that these two quartiles made up 50% of the population. So if we're actually interested in, which we probably are if we're going to model it as a continuous variable, we're interested in the entire group, we have to recognize that whatever the sample size we end up finding here was calculated using only 50% of the population. So say our calculation came out to 500, so we'd need 500 people in order to compare this 4th quartile to this 1st quartile. We'd have to recognize that we're only using 50% of the population, so if in reality we're interested in including this as a continuous variable, we want to be able to have the power to calculate, to be able to make inferences across the entire distribution. So since this is what we would need to find this in 50%, we just doubled it to be able to get the entire population, so we need 1,000. Another situation is if we have, say, 3 groups like low, medium, and high exposure that are probably not going to be evenly distributed. What we can do is compare those with the largest difference. So here we would be considering P1, the risk in the high exposure group, and P naught, the risk in the low exposure group. Whatever we were to find, say if we found a required sample size of 200, we'd have to recognize that we only used 70% of the population, like I said in the other one. So we'd have to increase the sample size to what would be needed to calculate 100% of the population. So basically this is rearranged from 200 divided by what gets 70%. So what is 270% of? And that's what we'd need to be able to include this medium exposure, which I'm guessing we'd have interest in. Yeah, so if we have a strong confounder, something we can do is inflate the sample size by 10% per strong confounder, because you'll notice that confounders weren't part of that previous description or any of those equations. Another situation is you might have cohort data that found incidence rather than like a risk. So that would be really anything that uses person time, so certain cohort studies and survival analysis. And you'll remember that P, P1, and P naught were all prevalences. For example, P was the number of diseased over the number of people at risk. Where incidence has time in the denominator, it's the number diseased over person time. A way to kind of estimate this crudely for the sake of sample size calculations is to multiply by the medium or mean follow-up time And you'll notice that when you multiply by time, time cancels out in the denominator, and we have an estimate of p.